Hello! Today we're going to be discussing moment of inertia, also referred to as rotational inertia. Rotational inertia is an object's resistance to rotation, just as its regular inertia was its resistance to a change in its motion. When we discussed inertia previously, we recognized that it was dependent solely upon an object's mass. In our rotational inertia, it will be dependent upon not only the mass, but also the radius or the length of an object as well. The variable that we use to represent rotational inertia is I. Okay, we'll also use I for current in a couple of weeks, but that's the one we're going to use right now. And our unit is kilograms times meters squared. We have several common objects which we'll keep using over and over again for rotational inertia, so let's talk about those relationships real quick. The first one we're going to look at is a point mass. It's in our discovery activity that we did. The point mass-like object was that clay blob on the end of our meter stick. Okay, so if we were rotating our meter stick at one end, so I'm going to draw the little axis of rotation down here, and we have our clay blob at the other end, the distance that the clay blob is from the axis of rotation we'll define as r. Okay. So the equation that we're going to be using for the point mass in terms of its rotational inertia is that I equals mr squared, where m is the mass of the point mass and r is its distance from the axis of rotation. We also looked at a hoop that would roll, and for a hoop, all of the mass is located around the outside, again, a distance r from the axis of rotation. Okay, and r in this case is the radius of the hoop. Okay, and the axis of rotation is going to be the center point. Okay, it spins around that. And our equation for a hoop is also I equals mr squared. Alright? For a disk, however, the mass is not solely around the outside, it's solid throughout. Okay, so if we were to look at a disk, we would see that it is full of mass. So in this case, looking at that blue circle, the mass would be all the way throughout. And therefore, we know that it's going to have a lower moment of inertia because the mass, or the distance to the mass, is less. So our moment of inertia for a disk is going to be I equals 1/2 mr squared. Okay? There's a very complicated equation that involves some calculus that we could use. However, we're going to save that for another time in another place. The two other things we're going to be looking at are a rod being rotated about its end, and then a rod being rotated about its center. Okay, when I say a rod being rotated about its end, I mean like a meter stick being held on one end and rotating around that. Okay, so if we hold a meter stick here on one end, rotate it around. Okay, there's really not a radius for that per se, so we're not going to use r for our variable. Instead, we're going to use L, where L is the length of the entire rod. Okay, and our equation for a rod about its end is that I equals 1/3 ml squared, where m is the mass of the rod and L is the total length of the rod. If we change our axis of rotation for a rod about its center, and these views could both be either side views or top views, it doesn't really matter. It could be spinning vertically or horizontally. And now our axis of rotation is here. We're still going to use the entire length L of our rod, and our relationship this time will be that I equals 1/12 ml squared. Okay? If we have multiple objects in a system, we will just add up the different objects that are present. Okay, so if we had, let's say, a rod with a point mass on one end, and we wanted to find the moment of inertia of the system relative, let's say it's being rotated about this end, we would just add up the individual moments of inertia of the rod and the mass. Okay, so not real difficult. Moments of inertia are always positive. They're not vector quantities. So whenever you want to find the moment of inertia of a multiple object system, all you have to do is just add up the individual moments of inertia.
Thanks.